Good day. Today, we will be talking about four main topics: rational functions, rational expressions, rational inequalities, and graphing rational functions. Rational functions. By definition, a rational function is a quotient of polynomials in which the denominator has a degree of at least 1. In other words, there must be a variable in the denominator and it should not equal to 0. The general form of a rational function is f of x equal to p of x, where p and q of x are polynomials, and again, q should not be equal to 0. Y equals to 2x plus 1 over x plus 5. Is this a rational function? Yes, it is a rational function. Here are more examples on rational function. Rational inequalities. Rational inequalities are inequalities that contain a rational expression such as 3 over 2x is greater than 1. Here are more examples on rational inequalities. The first step is to change our inequality as one quotient in the left and 0 on the right. Determine the critical points or the points where the rational expression will be 0 or undefined. 1 minus 1 equal to 0. Negative 3 plus 3 equal to 0. Critical points are 1 and negative 3. Then, use the critical points to divide the number line into intervals. Next is we test a value in each interval above the number line. Show the sign of each factor of the rational expression in each interval. Below the number line, show the sign of the quotient.
The numerator x minus 1. Since negative 4 will be the substitution of x in the numerator, this will become negative 4 minus 1, which will become negative 5. The same procedure can be done with the denominator. Substitute negative 4 to the x, which will become negative 4 plus 3, which is equal to negative 1. Interval negative 3 is lesser than x is lesser than 1. As the substitution of x is 0, we can reduce that into 0 minus 1 is equal to negative 1 in the numerator. The same procedure goes with the denominator. Substitute 0 with x and it will become 0 plus 3 is equivalent to positive 3. Interval x is greater than 1. The numerator x minus 1, replace x with number 2. So it will become 2 minus 1 equals into positive 1. Same procedure applies to the denominator x plus 3. Replace x with the number 2. 2 plus 3 is equal to positive 5. Determine the intervals where the inequality is correct. Write the solution in interval notation. X is lesser than negative 3 and x is greater than positive 1. For x over x minus 6 is less than 1. Change the inequality as one quotient is in the left and 0 on the right. Rewrite 1 as a fraction using the LCD. Subtract the numerators and place the difference over the common denominator. Simplify. Factor the numerator to show all factors. Find the critical points. X plus 2 equals 0 and x minus 6 equals 0. Our critical points are negative 2 and 6. Divide the number line into intervals. Now, we test a value for each interval. Above the number line, show the sign of each factor of the rational expression in each interval. Below the number line shows the sign of the quotient. 5 over x squared minus 2x minus 15 is greater than 0.
Factor the denominator.
Find the critical points. The critical points are negative 3 and 5. Use the critical points to divide the number line into intervals. Test values in each interval. Write the solution in interval notations. 1 over 3 minus 2 over x squared is less than 5 over 3x. Transpose 5 over 3x so that 0 is in the right. Rewrite to get each fraction with the LCD 3x square. Simplify. Subtract the numerator and place the difference over the common denominator. Factor the numerator. Find the critical points, which are the critical points are 0, 6, and negative 1. Use the critical points to divide the number line into intervals. Above the number line, show the sign of each factor in each interval. Below the number line, show the sign of the quotient. Final answer is negative 1, 0, and 0, 6. X plus 3 over x minus 5 is less than or equal to 0. Find the critical points. X plus 3 equals 0 and x minus 5 equals 0. The critical points are negative 3 and positive 5. Use the critical points to divide the number line into intervals. Test value in each interval. Write the solution in interval notation. Rational expressions. Rational expression is simply a quotient of two polynomials, or in other words, it is a fraction whose numerator and denominator are polynomials. Example of a rational expression: x squared plus 5 over x plus 2. The numerator is x squared plus 5 while the denominator is x plus 2. It is a rational expression because it has a ratio of two polynomials. Here are more examples of rational expression. Polynomial is a mathematical expression that contains two or more algebraic terms that are added, subtracted, or multiplied. There are three methods where we can solve rational expressions, namely, Method 1, converting to a common denominator. Method 2, multiplying through by the common denominator. And Method 3, by cross-multiplying. For example, 5 over x minus 1 over 3 equals to 1 over x. Multiply both sides by the LCD. Distribute, simplify, and then solve. Here, we were able to solve the equation by clearing the fractions by multiplying both sides of the equation by the least common denominator. Additional reminder, an equation that contains at least one rational expression is called a ratio equation. A rational expression is undefined when the denominator is 0. 2 minus 1 over x multiplied by x plus 1 equals to 3 over x plus 1. Begin by multiplying both sides by the LCD, x multiplied by x plus 1. So it will become 2x parentheses x plus 1 minus 1 equals 3x. Rearrange it. After distributing and dividing out the common factors, a quadratic equation remains. To solve it, rewrite it in standard form, factor, and then set each factor equal to 0. Extraneous solution. Solutions that doesn't solve the original equation. For example, x over x plus 2 plus 2 over x squared plus 5x plus 6 equal to 5 over x plus 3. factor all denominators and determine the LCD, in which case the LCD is x plus 2 and x plus 3. Identify the lowest common denominator. Multiply both sides of the equation by the LCD. Distribute carefully and then simplify. Solve the resulting equation, rewrite it in standard form, factor and then set each factor equal to 0. Check for extraneous solutions. Always substitute into the original equation or the factored equivalent. 3x over x squared plus 4 minus 2 over x plus 2 equal to 1 over x plus 2. Identify the LCD. First factor the denominators. Multiply both sides by the LCD. X plus 2 and x minus 2. Distribute carefully. False. No solution. Why? Because the equation is a contradiction and thus has no solution. Inconsistent. No variable for x minus x equal to 0. X over x minus 4 over x plus 5 equals to 36 over x squared plus x plus 20. Identify the LCD. First, factor the denominators. Multiply both sides of the equation by the LCD. In here, it is x minus 4 and x plus 5. Distribute carefully and then simplify. Solve the resulting equation, rewrite it in standard form, factor, and then set each factor equal to 0. Graphing rational functions. If f of x represents a rational expression, then y equals f of x is a rational function. To graph a rational function, first find values for which the function is undefined. A function is undefined for any values that would make any denominator become 0. Dashed lines are drawn on the graph for any values for which the rational function is undefined. These lines are called vertical asymptote lines. The graph of the rational function will get close to these vertical asymptote lines but will never intersect with them. How to graph rational functions? Find the intercepts if there are any. Remember that the y-intercept is given by 0, f of 0, and we find the x-intercepts by setting the numerator equal to 0 and solving. Find the vertical asymptotes by setting the denominator equal to 0 and solving. Find the horizontal asymptote if it exists using the fact above. The vertical asymptotes will divide the number line into regions. In each region, graph at least one point in each region. This point will tell us whether the graph above or below the horizontal asymptote, and if we need to, we should get several points to determine the general shape of the graph. Sketch the graph. Example number 1. F of x equal to 3x plus 6 over x minus 1. Find the intercepts of this equation. Finding the x and y intercepts. To get the x-intercept, change the numerator into a 0 equation. For the y, substitute 0 to the x to get our y-intercept. Finding the vertical asymptote. Remember to set the denominator to 0 so that you can transfer the constant. Finding the horizontal asymptote. The largest exponent in the numerator and the denominator of the equation is 1, and so by the fact there will be a horizontal asymptote. Finding the points. Substitute the chosen number for x in the equation to find the y and doesn't surpass and touch the asymptotes. Choose any number to substitute the x. It is suggested to choose lesser numbers. Vertical asymptote, horizontal asymptote.
Find graph.
3x plus 6 over x plus 3. Same with number 1, find the intercepts of this equation. To get the x-intercept, change the numerator into a 0 equation. For the y, substitute 0 to the x to get our y-intercept. Remember to set the denominator to 0 so that you can transfer the constant. Largest exponent in the numerator and denominator of the equation is 3, and so by the will be a the fact there will be a horizontal asymptote. And now in x we have negative 4, negative 5, negative 6, negative 2, negative 1, 1, and positive 4. For y, we've got 6, 4.5, 4, 0 is the intercept, 1.5, 2.25, and 3. And now we graph. Example number 3. X squared minus 4 over x squared minus 4x. Find the x and y intercept. Finding the asymptotes. We've got one vertical asymptote, but there may be more, so let's go through the process and see. X squared minus 4x equals x multiplied by x minus 4 equals 0. X equals 0 and x equals 4. We've got 2 again, and the three regions that we've got are x is less than 0, 0 is less than x is less than 4, and x is greater than 4. Next, the largest exponent in both the numerator and denominator is 2, so by the fact there will be a horizontal asymptote at the line. Y equals 1 over 1 equals 1. Example number 3. X squared minus 4 over x squared minus 4x. X squared minus 4 over x squared minus 4x. Finding the points. Now, one of the x-intercept is in the far left region, so we don't need any points there. The other x-intercept is in the middle region, so we'll need a point in the far right region, and as noted in the previous example, we will want to get a couple more points in the middle region to completely determine its behavior. Example number 4. 9 over x squared minus 9. Find the x and y-intercept. The y-intercept is negative 1. The number is a constant, so there won't be any x-intercept since the functions can never be 0. Find the asymptotes. Now, we'll have a vertical asymptote at x squared minus 9 equals to 0. X equals positive negative 3. In this case, we'll have 3 regions to our graph. X is lesser than negative 3, negative 3 is lesser than x is lesser than 3, and x is greater than positive 3. The largest exponent in the denominator is 2, and since there are no x in the numerator, the largest exponent is 0. So by the fact the x-axis will be a horizontal asymptote. In the x, we've got negative 4, negative 2, positive 2, and positive 4. While in the y, we've got 1.29, negative 1.8, negative 1.8, and 1.29. Example number 5. 4 over x minus 3. Find the intercept and the asymptote. The vertical asymptote is 3, while the horizontal asymptote is 0. Thank you for watching. Thanks for watching. Thank you for watching.